There are 30 multiple choice practice problems in Unit 2 on redox and electrochemistry. Looking at number 1, what is the oxidation number assigned to chlorine in sodium hypochlorite? Remind students that when we have a compound that the individual oxidation numbers must total 0. And that was one of our oxidation number rules. When we have a compound like this, and particularly oxygen that's in a polyatomic ion, hypochlorite ion in this case, oxygen will be assigned its most common oxidation number of -2. So we'll go ahead and assign that to oxygen. Looking at the metal sodium, it's a group 1 metal. It will be assigned, we think of sodium as a group 1 metal as a +1 ionic charge, and that will also be its oxidation number in this compound. So that leaves us with chlorine. The only possible value of chlorine would be +1, so we can add these three values together to get 0. Students, sometimes feel uncomfortable choosing a +1, which they're not familiar with for chlorine. But, again, this is an assigned oxidation number. It is not chlorine's normal charge, so the correct answer is B. Moving on to number 2, what is the oxidation number assigned to oxygen in OF2? In this case, this is, a little unusual. Students want oxygen to be the answer D, -2, because that is its most common value. However, this isn't a polyatomic ion. It is still a neutral compound, so we know that these oxidation numbers have to equal 0. And they need to remember one of the oxidation rules that said that fluorine must be assigned a -1 oxidation state. So there are 2 fluorines, so together they're each -1 or -2 overall. So that leaves us with oxygen, which seems unusual, but +2, which is answer C, is the correct value. In questions 3 and 4, the next questions, really show students why it's important to understand how to assign oxidation numbers. Because before we get into electrochemistry, we have to understand, how to identify substances that are oxidized and reduced in a reaction. So number 3, what element is oxidized? Again, the mnemonic devices mentioned in the notes are helpful, like oil rig or Leo the lion says grr, whichever one students prefer. Some use, it's their personal preference or yours. But if we're asked about oxidation, we're really focused on these. So oxidation involves loss of electrons or losing electrons is what's happening in oxidation. So, before I even go through and look at oxidation numbers, I've noticed the word oxidized, and I think the word loses goes with that, and then I noticed there are 2 answers that mention gaining. So I'm going to go ahead and mark those out because I'm not even going to consider those because there's no chance that is the answer. So that's just a way to narrow down the answer choices right off the bat. Moving on to coming up with the correct answer, A or C, we do need to assign individual oxidation numbers. So we can see it's either going to be iodine or sulfur. We start with iodine. It's a monatomic ion with an overall charge of -1, so that is its oxidation state. As a product, it's becoming an element. I2 is its elemental form, and so it's 0. So it's going from -1 to 0. And then we'll just go ahead and look at sulfur as well. So sulfur is in the sulfate ion, and again, in polyatomic ions, oxygen will be assigned an oxidation number of -2. So if there are 4 oxygens, that would be a total of -8 for all the oxygens. And this time, since we don't have a neutral compound, it's an ion, the overall charge must equal whatever that charge is, in this case, -2. So that gives us with a sulfur with an oxidation value of +6. So we have sulfur going from +6, and then in H2S, we can see hydrogen is acting, as a metal role. It must have a positive charge. So each hydrogen is +1, so it's a total of +2 for the hydrogen. So sulfur, therefore, would be -2 to end up with 0 once those 2 are added together. So we know that losing electrons causes the charge to actually go up in value because we're losing negatives. So if we notice that iodine goes from -1 to a higher value of 0, so therefore it must have been losing electrons and the answer. So we're going to pick A. If you notice, sulfur is actually going down in value, so that is reduction. So the answer for number 3, what element is oxidized, is A, iodine. It is losing 1 electron. Number 4 is involved in this same reaction. It's just asking which of these is the correct balancing of the half reaction of this iodide to iodine. With the balancing rules, first we balance the elements other than oxygen and hydrogen, then we deal with oxygen and hydrogen if needed, and then finally balancing with electrons to balance the charges. So as you can see, there are various answers here. Some have skipped steps, some have, just misinterpretations of steps. So the first step here, and I would get students to start from the beginning, like balance this half reaction for yourself and then find your answer instead of trying to, weed through what these answers are, because you might just choose the wrong answer just because you haven't actually worked it out for yourself. So looking at this, we can see that the iodines are not balanced, so we have to balance those. There are no oxygens and hydrogens to balance, so we'll move straight to balancing electrons. There are 2 -1s, so that is a -2 overall charge. So a lot of times students will forget this 2 and just assume this is -1, so that's a way to make a mistake. And then we know the element is overall 0. So to balance this, we could add 2 electrons to the products, and by doing that, we would have -2 on both sides. So we know that would be the balanced half reaction. And if we look through the answers, the only one that is correct is C. D looks pretty good, but it's not simplified, and we do need our answers in lowest terms, so we're going to pick answer C. In question 5, I think this is a good example of giving students an opportunity of being able to apply their knowledge of assigning oxidation numbers, recognizing that change in oxidation number, and then also being able to recognize when there is no change in oxidation number. So for which of the following is not an oxidation reduction reaction, make sure students have, you give them the clue of looking for an element. Obviously an element is going to have an oxidation number of 0. If you look at A, we see that we have fluorine as an element F2 and changing to F- in the KF compound. So as an element goes through the reaction, it has to have a change in oxidation number, and that's a huge clue that we have a redox reaction. So we can see that A is redox. The fluorine changes as well as bromine. For B, sodium is an element. Oxidation number 0 going to +1 in NaCl, along with zinc going from +2 to 0. So A and B are both redox, and then we get to C, and we have a synthesis reaction, 2 elements forming a compound, so no question that's got to be redox as well, so that leaves us with D. D must be the answer. And if students go through and assign, this could be a good practice problem, and require them to assign oxidation numbers to every species, and then we'll see that none of the atoms do change oxidation number, so D is the answer. Moving on to 6, which of the following is true about the reaction above? And as you evaluate the answers, you see that A and B both claim this is an acid-base reaction, where C and D say this is redox. Based on students' previous knowledge, perhaps from their first year chemistry class, they might know that sulfuric acid is a strong acid. But, again, Ki, hopefully they would realize, is a base. Is not a base. So A and B really are not going to be possible answers here. The other question, if students aren't sure about what a Bronsted-Lowry acid-base reaction is, they can go ahead and evaluate C and D, because again, like we saw in 5, if this is not oxidation reduction, then they would know it, they could eliminate those two choices. But as we'll see that this is a redox reaction, the I in Ki is a -1 oxidation state. As it goes to the element I2, it is 0. So you have a -1 to 0 change, so there is a loss of an electron. So if we look at the answers here, we can already tell that C would not be correct because I is not gaining an electron. It must be D, and if we want to check the sulfur, we'll see that in sulfuric acid, the sulfur does have a +6 oxidation state, and as it goes to H2S, it has a -2 oxidation state, so that is a gain of 8 electrons. In question 7, we're given an unbalanced half reaction, and we're asked to balance how many electrons would be required to balance, and are they needed on the reactant or product side. Really, if students just tried to go in and balance electrons, then they're not going to be able to come up with a valid answer. They hopefully would recognize that the oxygens have not been balanced. So if we notice the permanganate ion has 4 oxygens, we'd have to add a 4 coefficient in front of water. And once that's been done, we'd also need to balance the hydrogen. So now we would have, with 4 water molecules, just put that up top, with 4 water molecules, we would have 8 total hydrogens on the product side. So we would need to balance that with an 8 in front of the hydrogen ion. Since that's been done, now we can actually come up with the total charge on each side of the reaction. The reactant side, we have the -1 from the permanganate ion added to a +8 from the hydrogen. So overall, on the reactant side, we have a charge right now of +7. And on the product side, water is neutral, so that overall charge is just +2. So we have +7 on the reactant side and +2 on the product side. So to get those charges to be the same on both sides, we would need to add electrons to reduce that +7 on the reactant side. So we would need electrons, and the correct amount would be 5 electrons. Because if we add 5 negatives to +7, then we would equal +2, and both sides would be the same. So that would give us the answer of C being correct. Moving on to 8, it says identify the correct balance half reaction above. We have this oxalate ion and carbon dioxide, and I like this example because it shows students sometimes, these half reaction balances can get a little complicated, but other times, one coefficient balances, several, more than one atom. So this is a case in this one. So if we look at the oxalate ion, we see the 2 carbons, and we only have 1 carbon in carbon dioxide. So if we add a 2 with the carbon dioxide, that gives us 2 carbons on each side. And now we, as we typically do, we go to oxygens next. We see the oxalate ion has 4 oxygens, and now the carbon dioxide side with the 2 coefficient, 2 times 2, we have 4 oxygens. So there's really no need to add water or hydrogen ions. So really C and D can be eliminated. Those, some students may not recognize that the oxygens are now balanced, and so they might keep trying to add other things. So really our next step is to go straight to our electrons, and we see a -2 charge on the reactant sides, and the products are a neutral compound, so it is 0. So if we add 2 electrons to the product side, then that should that does balance, and the correct answer is A. Beginning with questions 9 and 10, we get into some questions that involve specific knowledge of a galvanic cell and the parts and its parts. So we're given a reaction, number 9. It says which answer accurately indicates the process that occurs at the anode. The helpful mnemonic devices, I think a lot of students really like those. Red Cat and Anox. Hopefully they would remember, anox refers to oxidation and occurs at the anode. So for 9, since we're looking for something that's oxidized, we again can eliminate 2 answers that are mentioning the wrong process. So A mentions reduction, which we know does not happen at the anode, and C also mentions reduction. So narrowing down the choices does help students, come to the correct conclusion. So looking at the reaction, we're looking for oxidation, which we know a substance is losing electrons, and it actually is going up in charge or up in oxidation number. The oxidation number is increasing. So we know zinc is 0 since it's an element. Copper is +2, that is its ionic charge. And zinc is +2, and then copper as a product is also 0. So if we go from what A says, zinc is oxidized to Zn2+, zinc is 0, and it is going up to a higher value of +2, so we would know that B is the correct answer. Just to go through the other answer, D, it says that copper is oxidized to Cu. If copper is going from +2 down to 0, it is a reduction in value, which indicates it is actually reduction. So that also is not going to be the answer. So our answer is B. Number 10 also goes along with the same reaction. As the copper 2+ ion reacts to form copper as a product, what observation would indicate a reaction was taking place in the copper half cell? No longer are colors asked on the exam, because you might know the copper 2+ ion in solution has a really pretty blue color, so that the color of the solution would be changing, but we're not going to be asked that question because that's beyond the scope of the new exam. So our choices are an odor would be produced. If we look at the products, there are no gases, so that would not be a good choice. And then we have 2 answers, B and C, about the mass of the copper changing, and then D, no observation would be evident. Most likely, if they're asking what observation would indicate that reaction was taking place, there's probably going to be one to choose from, so D is probably not going to be a good choice. So if we look at B, what is happening to the copper electrode? Well, we just said earlier that copper 2+ is reduced to become copper the element. That when reduction's happening and is producing a solid, literally that ion is coming out of the solution, gaining 2 electrons, and plating on top of that existing copper electrode, which means it would be increasing in mass or gaining mass. So the answer is C. In questions 11 and 12, we're given 2 half reactions, one involving silver and one involving zinc, and their individual reduction potentials. The question 11 says, what is the standard cell potential when a galvanic cell is constructed using the half reactions above? A galvanic cell, students are required to know that that is a thermodynamically favorable reaction that should have a positive overall cell potential. So if we look at the 2 cell potentials given, we see that silver is positive 0.80 volts and the zinc is negative 0.76 volts. So for this reaction, the higher reduction potential, since this is a galvanic cell, will stay reduction. So silver ion will be reduced to solid silver, and it's the zinc half reaction that will be reversed. So when we have a cell potential, when we are calculating the total cell potential, we take the reduction potential and we add it to the oxidation potential. But since zinc currently is listed as reduction, we would have to reverse that reaction, and by reversing that reaction, I'm just going to put an R for reverse, we change the sign, because as the reaction is reversed, that also changes the sign. So now we have a positive 7.76 volts, and so as we add those together, we can see we do get a positive overall cell potential, which has to happen for a galvanic cell. and literally just having to add those two values together, 1.56 volts. Number 12, we have this same cell. It is a galvanic cell. Which way the direction of the electrons flowing in the wire? This was another mnemonic device, Fat Cat. It's kind of a stretch, but it's the flow of electrons go from the anode to the cathode. So again, knowing what's going on at both of those cells, anode and cathode, what process is occurring there, and which will help us understand how electrons are moving through the wire. So we said zinc was oxidized to become the zinc 2+ ion. Oxidation is the anode, anox. So, and Fat Cat tells us the flow of electrons is from the anode to the anode to the cathode, which makes sense because oxidation is where electrons are lost. Those lost electrons are the ones that will travel through the wire to the cathode, which will be gained by the silver ion. So, the answer is A. Electrons leave the zinc half cell and travel to the silver half cell. This next set of questions, questions 13 through 17, all use these half reactions listed above, and that's kind of a typical question setup for many of the questions on the AP Chem exam. Looking at 13, which of the following reactions below would be thermodynamically favorable? And this really brings in their knowledge of delta G, and knowing that for delta G to be negative, which is a thermodynamically favorable situation, that the cell potential would have to be positive. So the easiest way really is just for students to look at this balanced reaction that's given and see what has been altered to the half reactions above, because all the half reactions we have are reduction, and for all these redox reactions, obviously it's going to involve one reduction half reaction, and the other half reaction would have been reversed to be oxidation. So if we look at A, we see that the cadmium ion half reaction is left reduction, which would leave it as a negative 0.4 volts. And if you look, notice the copper has been reversed so that copper solid is a reactant. So if we reverse the copper half reaction, in this case it's going to become a negative 0.52. So for it to be thermodynamically favorable, when I add the 0.4 volts and the negative 0.52, my overall answer is going to be negative, and so I know that that's an overall cell potential that's negative, and that would not be the answer. So I'm going to keep going. I know it can't be A. For the next situation, we have the manganese ion going to solid manganese, which is the second half reaction. It is staying reduction at negative 1.18 volts, and that the copper half reaction is being reversed again as it was in part A. So again, when it's reversed to be oxidation, that half reaction potential also gets reversed. So if I'm adding a negative to another negative, obviously I'm going to get another negative total. That also would be thermodynamically unfavorable and therefore not the answer. Going on to C, I noticed that now we have the cadmium half reaction again, and it's staying reduction since it's in the same form as its half reaction, and it's the manganese half reaction that's been reversed. So if we have cadmium as negative 0.4 volts, that is staying its same reduction potential, and the manganese half reaction is getting reversed. That makes it go from negative 1.18 volts to positive 1.18 volts. And so when I add positive 1.18 volts to negative 0.40, I do get a positive total. So I'm very interested in C. That seems like I'll check D to make sure I haven't made a mistake, but C is looking like, so far that's the only one that's had a positive overall potential. Moving on just to look at what D is presenting us with, I noticed that copper is stayed 0.52 volts, it's staying reduction, and that the iron half reaction is being reversed. And I do see that when I reverse the iron half reaction, that it does become negative. So I have a negative 0.77 volts plus the positive 0.52 volts, and again that negative value, having that negative value causes that total to be negative, so I can confirm that the answer is C. And in 14, which combination would produce the highest voltage for the galvanic cell? And if you think about it, the highest, the higher reduction potential stays reduction, and the lowest reduction potential is the one that gets reversed to be oxidation. I'm really going to be looking for extremes here. If I want the highest voltage, I want to pick the most positive value that's given, and I want to pick the lowest value of all those given. So if I look at the information I'm given, I have this iron, I can see is the most positive value, and then the lowest value would be the most negative, which is the manganese half reaction. So when the manganese half reaction becomes oxidation, its potential gets reversed to positive. Oops, had a little issue. To positive 1.18 volts. So we can see that it would be this iron, Fe3 plus, would be the reactant in one half reaction, and that the other reactant would be manganese. So that would be answer A. Those are the components of the cell, part A. In question 15, we're still in this, set of answers that goes with, set of questions that goes with the half reactions given above. And for this one, it says, now we're making a galvanic cell with the cadmium half reaction and the copper half reaction. Specify the cathode. So looking at those two, we've got a negative 0.40 potential, and we've got a positive 0.52. So again, the higher value will stay reduction, so we know that the copper ion, copper plus 1, will be reduced, and that it's the cadmium half reaction that will be reversed, so to be oxidation. So just knowing, which is going to be stay reduction and which one's going to be reversed to be oxidation does help us answer this question, because it says specify the cathode, and we know from the mnemonic device REDCAT that the cathode is where reduction occurs, so we want to look for the copper, the information about copper, and that will help us to choose the right answer. Just going to slide this up. So copper would gain electrons, and again, this is another case where you could, before even noticing the answers above, you definitely could eliminate the losing answers, since the anode is where electrons are lost. So cathode, we know that, as we can confirm from above, it's the cathode electrode where the electrons would be gained. Moving on to 16. Galvanic cell was made using half cells of iron, that combination, the iron ions, and manganese. What would be the initial reading on the voltmeter? So again, this is, each question is asking just a little bit different take on the same information. So if we're looking at the iron half reaction and the manganese half reaction, we can see that the iron half reaction looks like it has a higher positive potential. So if its higher positive potential is, I'm just going to draw an arrow, 0.77 volts, and manganese is lower, so it's the one that will have to be reversed, so it will be positive 1.18 volts. So as we said earlier, to get the overall cell potential, we take the reduction potential, which is given here. We're going to add it to that oxidation potential that we come up with, and so we can choose our final answer as C, positive 1.95 volts. And the last question involved with those half reactions above is asking what is the value of N for the galvanic cell containing half cells composed of those iron ions and the manganese ions that we just saw. This N, if since students have been learning about delta G, that is directly used when they are solving negative N. They're solving this delta G formula. So really we're asking about N, and it's defined on the formula sheet. It's the moles of electrons that are transferred in these redox reactions. So, it's hopefully students will get, this will become an easy thing for them to come up with. I think the hardest thing is, manganese has 2 electrons that it's going to be losing once, because we reverse that, and then this iron ion 3+ ion is only gaining 1. So sometimes students aren't sure what to do with that, but really what they need to remember about N is that N is always the balanced number of moles of electrons that allows for those electrons to cancel out when the half reactions are added together. So for answer A, 1 or 2, it has to be one value. It couldn't be either of those. And if you have to balance 1 electron and 2, then that balanced value would be 2. So we would have to double the iron ion half reaction so that there would be a transfer of 2 electrons. So the answer here is C. In 18, it says, what happens to the cell voltage of a galvanic cell if the potassium nitrate contained in the salt bridge is replaced with deionized water? This really, hopefully students are really understanding what's going on with the salt bridge. The whole purpose of the salt bridge is to provide a soluble salt, which are ions, cations and anions that can flow into corresponding cells to neutralize charge so that electrons can flow. So, KNO3 is a great choice. It's a spectator. They're both K+ and nitrate ions are both spectator ions. They're not going to form precipitates with any other ions that are already in the solution in the either cells. And so, what would be the change for water? And the answer would be B. There would be no voltage. The water would be unable to neutralize charges, and the electrons would not be able to flow. We do need cations and anions. Cations would flow to the cathode, and anions would flow to the anode, and the water would not be able to do that. In question 19, it's asking about this reaction and which statement is correct. And, questions like this, students really need to go through each answer choice and really evaluate what's going on in this reduction half reaction. As I say reduction, it's good to note that the 10 electrons are on the left side, so these are gained electrons. So one thing to note, just right off the bat, even before we worry about assigning oxidation numbers, is that A does state that the bromate ion is undergoing oxidation at the anode, and we can, hopefully you can help them notice that this is reduction, so any statements about oxidation are not going to really fit. And then if you look at C, I did want to address this because if you notice, bromine is a product, and we do know that this is being, the only information we have is this is a reduction half reaction. So no products are going to be oxidized and reduced. Those are results of oxidation and reduction. So again, we would also mark out C. So really it comes down to B and D, which means that we need to identify if B is the correct change in oxidation state, but we should know that D looks pretty good. So at this point, let's go ahead and evaluate to see if what's given in part B even makes sense. So if we know that the overall oxidation, the overall charge of a brown ion is -1, and in polyatomic ions, the oxygen's always -2. The oxygen group is going to be -6. As we see, the only thing that would work here would be bromine is +5. So we can see that B will not work because it's stating that bromine would be -1 in that ion, and that's incorrect. So we do know that D is the correct answer. Moving on to number 20. Hopefully students will recognize that they have a balanced overall reaction of M and the zinc ion, and then they have a half reaction for the zinc ion, and then also the question is about determining the standard reduction potential for the this unknown metal 3+ ions reduction. And so the key here is reduction potential. And when students are given a question like this, unfortunately, if you look at the answers, the correct answer and the answer that looks really good will have a difference in their sign. So a lot of students will pick the answer with the wrong sign. So if we look at the overall reaction and the two half reactions that are given, we can see that the zinc ion is reduced in the overall, so we know that this value will stay what it is in our calculation. And then we notice that this M3+ ion is actually a product in the overall, so that this is the half reaction that becomes oxidation and is reversed. Okay, so when we set up our math, we've got our overall cell potential equaling our reduction potential plus our oxidation potential, okay, whatever that is. So when we solve this for oxidation, we're going to get a positive 1.66 volts, which you see as an answer. But again, going back to the information, what is the standard reduction potential? And that is why, since this is oxidation, it must have been C, which would have been negative 1.66, which if you go back and think about when we have a galvanic cell, we always reverse the lower potential, so that would make sense that the M3 plus half reaction got reversed to be oxidation, since it is more negative than the zinc ion's reduction potential. In questions 21 through 25, we have a diagram of a galvanic cell, and students should notice that since there is a voltmeter, we have two separate containers. And as we're reading the information under the diagram, we need to help students recognize that vital information is probably contained in this, and again, sometimes they're so anxious to get to the question they don't read carefully, so they really do need to read these sentences, because our ability to solve this problem is based on our knowledge of what's given here. So it says a strip of tin and a strip of unknown metal X are used as electrodes. When the switch is closed, and here's the key, the mass of the tin electrode increases. So if they don't recognize that, then they're not going to be able to decide what's going on with these half reactions, because as you see underneath, we only have one of the reduction potentials given. So if the mass of the tin electrode is increasing, that is telling us that solid tin is a product. So we can see that this tin ion is going to be reduced. So that is our reduction half reaction. If we know what's reduction, so this is going to stay reduction. And we know that that's that cathode, so that's our red cat. And so the question 21, which electrode is the anode? It would have to be B, which is X. Okay, for 22, if the standard cell potential is positive 0.60 volts, what is the standard reduction potential in volts for the X half reaction? So again, as we saw previously, we have the total voltage. We know that the tin ion will be reduced to solid tin, so that is its reduction potential. And we're solving first for oxidation. Okay, so when we solve for oxidation, adding that to the other side, we see it as a positive 74 volts. However, it's asking again, this is the key word, reduction potential. So the answer is D, negative 0.7 volts. And again, that does make sense. It's more negative. That's why X is being oxidized and 10 is being reduced. Moving on to 23, this still, 23, 24, and 25 still go along with that galvanic cell diagram that was given on the previous page. This question, which of the following would be the correct setup to solve for delta G naught? Again, from our formula sheet, we have our formula. As we can see in the answer choices, all choices involve 0.60 volts, which was the given cell potential. One common mistake students make is they might try to plug in just in a common error would be to plug in one of the reduction potentials, possibly the one they solved for. But here that's been, I'm helping them out by giving them all the same answer choices. However, really what we're trying to evaluate here is, do they know the correct sign that should be achieved by solving this formula, and do they have the correct number of balanced electrons? So we saw that the 10-2+ ion was being reduced to 10, so that was a transfer of 2 electrons, and in the other half reaction, when it was reversed, we had the X metal being oxidized to X3+ ion. So we have a loss of 3 and a gain of 2, which obviously won't work with the law of conservation of matter or mass. So we need to choose an answer that has a balanced number of electrons. So the balancing of 2 and 3 would be 6. C is there just to see if they understand that we do have to have this negative sign from the formula, because once we solve this with a positive cell potential, delta G would have to be negative. So hopefully they will choose A, and that is the correct answer. Moving on to 24, if the 10-2+ ion is changed from 1 molar to 2 molar, how will the cell, and this is, notice there's no not sign, how would the non-standard cell potential change? Okay, so if the molarities, standard conditions involve 1 molar solutions, which is what we've seen to this point. In this case, the 10-2+ ion has been changed, and we have to really think about if we had this balanced reaction, where are the ions on either side of the reaction? So our 10 ion, was reduced, and if we were balancing this, it would have a 3. Our X was oxidized, and it had a transfer of 2 electrons, so it would have a 2 to keep that balanced. And then as products, we would have 3 solid 10 atoms and 2 X3+ ions. So notice that this is balanced. We have a positive 6 charge on this side and as well on that side, so we can tell the balancing of 6 electrons did work. What we need to really look at here is the ratio of products that are ions over reactants. So the ratio here, based on the knowledge of only the 10 ion was changed, so that means the X ions concentration would remain 1, and the 10 ions concentration was changed to 2. This really involves the Nernst equation. Again, that is not on the formula sheet at this point. It was removed when the exam was changed. Technically, if this was, students really aren't going to be expected to realize this, but the coefficients, and this is in the notes, are supposed to be the coefficients are supposed to be exponents here. Okay, but since this isn't a true math question, the understanding they need to know is that 1 over a higher value, we have a fraction here, either if they think of it as 1 over 2 or if they think of it as 1 over 8, it doesn't matter, it's less than 1. So this is what they need to think of, is Q is less than 1. Okay, so what's going to happen is, if you actually solve the Nernst equation, is when you take a log of a number less than 1, you get a negative value. So if you solve the Nernst equation, you would take the standard cell potential minus this term you got after you did the rest of the math. So if you're subtracting a negative, you're actually adding. So the cell potential would actually go up. And so our answer, we're down to C. If we have a ratio that's less than 1, we're actually going to have a higher cell potential. And the reason is because we have more reactants present. So more reactants can produce more voltage. 25, what is the expected value of the equilibrium constant K for the cell above? Again, this just goes back to understanding really what it means to have a galvanic cell. So we have a positive cell potential, standard cell potential. We have a negative delta G because this is thermodynamically favorable. This is a battery, it's happening on its own. And therefore K would have to be greater than 1, because again, K is the equilibrium constant. It is the same ratio as Q. It's just K is when you would have equilibrium concentration. So K is that same ratio, products of reactants. If a reaction is going forward, no question, producing voltage, it's producing products, as evidenced by that voltage being produced. So it's what we say, products are favored. So our answer is D. In the last group of questions, 26 through 30, there's a diagram, and just looking at this picture, students should be able to tell that that power supply is labeled. There's one container. There's no salt bridge, so this must be an electrolytic cell or electrolysis. So. And even in the wording, as you notice, it says direct current power supply is connected. Again, reading every detail is hugely important, and it's going to give them some huge clues as to what's going on here. So the first question is, what is the direction of the electron flow in the wire, which means we would have to know what's oxidized and reduced. So as the cell operates, copper metal is deposited on one electrode, and they actually have a huge clue for us here. So this half reaction is actually what's happening at that electrode, as mentioned in the wording and on the diagram. And the other thing, it says oxygen gas is produced at the other electrode. So those are supposed to be bubbles, and that's oxygen gas that's a product. So looking at these two half reactions, we know that this copper half reaction will stay just like it is, and that's what we went through in the notes in the PowerPoint, that in electrolysis it's the opposite of what a galvanic cell would be. So our lower reduction potential will stay reduction, and it's that higher reduction potential that's going to get reversed. So this top half reaction, notice oxygen gas is a reactant, and we need it to be a product. So that's going to get reversed, the R for reverse, to be oxidation. So our cell, it was positive. And now we're going to, it's going to be negative 1.23 volts when we reverse that half reaction. So oxygen gas can be a product. So now that we kind of understand all the details going on, 26, what is the direction of the electron flow in the wire? Nothing's changed. Our mnemonic device, FATCAT, can help us understand that the flow of electrons is still from the anode to the cathode. So we know by reversing this oxygen half reaction that is the anode. So we need to just look for the correct wording once we understand really what's going on. So it looks like D is going to be our correct answer. It's going to be from oxygen to copper, so we could have, taken a close look at C and D once we realized what was going on. And we need to know, we also know that, as we talked about earlier, and ox. So whatever's the anode is where the electrons are being lost. And so these electrons would actually, if you were asked to draw like in a free response, the electrons would actually be coming from the oxygen and traveling through the wire to the cathode. So the answer is D. 27, which of the following is the correct balanced net ionic equation for the electrolysis reaction that occurs in the cell? So hopefully students realize this is electrolysis. If not, they're being told or reminded that it is. So again, it's thinking about what stays reduction, what was reversed to be oxidation. And we know that as if you paid attention to the reading and what was going on in the previous question and in the prompt, we could see that in the copper ion is reduced. So we're looking for the copper ion to be a reactant. And if we look at A, B, C, and D, we can see that only C and D involve copper ion as a reactant. So we're going to go ahead and eliminate A and B. And then the other thing is we know that the oxygen gas needs to also be a product. So that means the water, when it was reversed, became the oxygen gas, as you notice in C and D, is a product. And water is the reactant once that reaction was reversed. So now we're down to which one of these is correct, because they both look very similar, and it really comes down to did the student think about balancing electrons? The water, now that its oxidation is reversed, it is losing 4 electrons, yet the copper is only gaining 2. So that's why that the copper reaction has these 2 coefficients. It did need to be doubled to balance it, so we do have the answer of C. On 28, it says, which of the following is the correct standard cell potential for the reaction? A good rule of thumb here is we know this is electrolysis, and hopefully the student would remember that there's no way it could be positive, so we could go ahead and eliminate those 2. And then we could just go back to the previous values and do the math. So we do need to, the math is no different. So we would have our standard cell potential is going to be equal to the copper. Go back and look at that. We have copper state reduction at 0.34 volts plus our water half reaction did get reversed, so now it is negative 1.23. So when we add those 2 together, we can see that the only answer that would work would be B. Moving on to 29, it says an electric current of 2 amps passes through the cell for 40 minutes. How many coulombs of charge are moving through the wire? There's a couple ways to approach this. On our formula sheet, there is the relationship between current, coulombs of charge, which is the charge on electrons, and time. So this is a rate. As we can tell, we have amps is the unit for current. So we have 2 amps for I, and then we have a time. Amps, students need to remember, and this is also on your formula sheet, that amps are coulombs per second. So these minutes aren't going to really work for us right now. So there are a couple ways to do this. This could be done as a straight dimensional analysis, or maybe changing minutes to seconds and then plugging into this formula. So either way will work. I'll go ahead and just do it as a dimensional analysis problem, because I do know that 2 amps is really 2 coulombs per second. So I'm going to go ahead and change 40 minutes to seconds. And again, we don't have a calculator, but that's all right. And so I need to cancel out seconds. This is what I'm going to be using, and I'm solving for coulombs. So I could either go back and plug in, the 2 amps here, and then plug in my time, which would be 2,400 seconds at this point, because my minutes are canceling out. Or I could also just do dimensional analysis. So either way works. Some students have a preference. A lot of people like to do, I prefer dimensional analysis, but if having this formula on the formula sheet is more helpful, that might be the way to go. So we can do this math in our head. So 40 times 60 is going to be 2400 times 2. That'll give us our 4800 coulombs. And so that is going to be B. And then the last question here, select the correct relationship for the electrolytic cell above. Again, this is just their knowledge of what this means to have an electrolysis reaction. And really from the picture, you can see that that power supply is present. It's mentioned in that prompt as well. So anytime we have to add energy to make a reaction occur, we know that is really an unfavorable reaction. So we just need to pick the correct wording. We know delta G needs to be positive. Then you really need to know the difference in these two signs. So we're going to pick A. Delta G is positive since the reaction is thermodynamically unfavorable. If students are, again, really you don't have to memorize this. If they just went back to their delta G formula and they plug in this negative cell potential, so if they just plug in negative 0.89 volts, the moles are going to be 4 Faraday's constants on the formula sheet, 96,045 coulombs per mole of electrons. Again, multiplying a negative times a negative, delta G is going to have to be positive. So hopefully they can come up with that relationship either by deducing it from the math or just knowing that information.